Last week, in the last segment, we saw how to compute the minimum spanning tree in a graph, in a weighted graph. And we showed proofs of why particular algorithms like Prim's algorithm and Kruskal's algorithm work for this problem. This week, we're going to look at a different problem on weighted directed graphs. And this is the problem of finding shortest paths in graphs. It's also a very important problem that arises in many places. For example, when you use Google Maps or Waze or any other application to navigate your way through a city, the app is probably solving a shortest path problem from your current location to your destination and telling you what's the best path to get to the destination. Similarly, when you're sending email from your host to some other recipient on the internet, there's some algorithm deep down in the internet that's computing the best path to route your email through to get to the destination. So that is also solving a shortest path problem. So you can see that there are lots of places where shortest path problems arise. And so in this segment and the next couple, we will see different variations of the shortest path problem and different algorithms for solving these variations. So we will, as I said, we will use weighted graphs. The weight will be the distance of an edge in this case. The distance could represent cost, it could represent various other parameters, we don't care, but it's just a number. But the graphs are directed now. Why? Because you might have one-way streets in a city, you might have upload and download times that are very different on internet links and so on. So it's good to treat traffic flowing one way differently from traffic flowing the other way. And if you really want a link to be two ways, you can put two directed edges pointing in opposite directions to represent that two-way link as well. So using a directed graph is without loss of generality. So the first shortest path problem we're going to look at is the single source shortest path problem. So in this problem, you're given a weighted directed graph as shown in this figure. And you're also given a special vertex called the source. That's marked by the letter S here. This is the source. And in the single source shortest path problem, you want to find the shortest path from the source to every other vertex in the graph. And for now, let's assume that all the edge weights are positive, which makes a lot of sense, as I said, in a number of settings. For example, you couldn't traverse a road in negative time. It would take you some positive time to go from one end to the other of the road. So it makes a lot of sense to make all the weights positive. There will be occasions where we want the edge weights to be negative, and we will talk about that later. So we're going to take a greedy approach to solving the single source shortest path problem. And we ask ourselves the usual question, the greedy, is there a top level decision we can make now that we can be certain of, meaning this is the right decision in the optimal solution? So specifically, realize that shortest path from a node from the source S to any other node could consist of one edge or two edges or three edges, depending on the weights of these edges. So the shortest path to a vertex could be one, two, or three edges. So is there a vertex for which we can be sure of the shortest path right away? This is the greedy choice that we want to make in the beginning. Well, of course, there is the node S itself, because the shortest path to S, there's one of length 0 that doesn't go anywhere. It just stops right where it starts, and that's the shortest path to S of length 0. And clearly, if all the edge weights in the graph are positive, 0 is the best you can do for the shortest path. So we've already got the shortest path to S. That's good. But can we go a little further with that greedy choice? Can we make the decision a little bit more non-trivial? Specifically, is there a neighbor of the node S for which we can be sure the shortest path is a single edge? So if you look at this picture here, S has outgoing edges to two vertices, to B. This is the outgoing edge to B, and this is the outgoing edge to A. Notice that the edge from D to S is incoming into S, so we can't use that to get out of S. So S has two outgoing edges, SB and SA. Can we be sure that one of them is in fact the shortest path to that vertex, B or A? Well, the claim is that the neighbor A that is closest to S, for the neighbor A that is closest to S, the shortest path from S to A must consist of the single edge SA of weight 1. Why is that? Well, if the shortest path did something else, if it took some other edge out of S, it has to take some other edge out of S, and then continue on to A. But that first edge that the shortest path would take out of S already costs at least as much as the edge SA, which is the total length of the shortest path to A if you took the edge SA. So clearly, no other path can beat just going straight from S to A, where A is, of course, the neighbor that has the smallest weight edge from S. So we can say that the distance from S to A is exactly D of A, which is the weight of the SA edge, which is 1 in this case. Okay, so the bottom line is that you can make a greedy decision about that neighbor of S which is closest to it. We can definitely say that the shortest path to that neighbor is the direct edge from S to that neighbor. Again, this only applies if all edge weights are positive. So now we've got the shortest path from S to A marked in red here. What is the next vertex for which we know the shortest path? And this should remind you a little bit of the structure of Prim's algorithm for minimum spanning tree, where recall that we divided the vertices into two parts. Initially, one part had only one vertex, and all the other vertices were in the other part. And we successively found one vertex to bring over from the big part to the part that started out with one vertex. So here in the shortest path algorithm, we initially start out with just the vertex S in one part. Now we found that the edge from S to A is the shortest path from S to A. So now we've determined the shortest path from S to A. So now we make that part containing S a little bigger. It contains S and A. And we ask ourselves, which other vertex can we bring into this part? For which vertex can we say the shortest path is known? Well, if you look at the picture here, from S and A, you can get to B. So the cost of getting to B, the best cost of getting to B is not going directly from S to B. It's because the weight of the SB edge is 4. The best way to get from this side of the cut, which consists of SA, to B is actually to go from S to A for a cost of 1, and then to go from A to B for a cost of 2, leading to a total cost of 3. So that is the shortest path we can see to B. Now for D, the other possibility is to get to D, and that would cost 1 plus 5, which is 6, which is more than 3. So it looks like B is the vertex that has the shortest path that has all of its intermediate vertices on the S side. So we will say that B is the next vertex to bring in, and the cost 2 edge from A to B is what's going to be used on the shortest path from S to B. So the shortest path is the length 3 path. So now we've got the cut consisting of SAB on one side and all the other vertices on the other side, and we ask the question, which vertex to bring in next? And again, we have a few choices. We could either bring in D or C. The cost of bringing in D would be, you have to get from S to A to, the best cost of bringing in D is to go from S to A to B to D. So that would be like so. And the cost of that path is 1 plus 2 plus 2, which is 5. The cost of bringing in C, on the other hand, is also follow the S to A to B path, but here you branch this way. And so the cost is 1 plus 2 plus 2, which is 5, and that's the best cost we can find. So we should bring C into that side, which we do for the total cost of 4. Sorry, I said 5 earlier, but in fact this edge is of weight 1, so the total cost is only 4. The BC edge is of weight 1. So we've brought C in, and we continue in this manner. Now we realize that D is the thing we can bring in next, and finally we bring in T of weight 1. So now we've found shortest paths from S to every other vertex in the graph, and the entire structure of shortest paths is represented by the tree of red edges shown here. It is the shortest path structure is also a tree of all the shortest paths leading out of S. This is called Dijkstra's algorithm, after the inventor, Edgar Dijkstra. And this is a greedy algorithm that repeatedly chooses the next vertex to which the shortest path is known. So how does it work? Let's go through the description of the algorithm at a more abstract level rather than based on that example. So Dijkstra's algorithm maintains a set S of vertices, for which, capital S of vertices, for which the shortest path from little s is known. So all the vertices in capital S are going to be like are going to be such that the shortest path from little s to those vertices is already known. Initially, they said capital S consists of just the single vertex little s. So capital S is just the single source vertex. And why? Because we know the shortest path from little s to little s. It's the empty path of length 0. So initially, that's all we know. Then Dijkstra's algorithm works like this. For each vertex v in the rest of the graph, so here is the one side has little s in it, and the rest of the graph is v minus s, capital S, because this is the little s, the capital S side. So for each vertex v in v minus s, we maintain a distance, a provisional distance. It's not the final distance from s to v, but a provisional distance d of v, which is going to be the length of the shortest path to v passing only through vertices in S. So we're only interested in such paths, and Dijkstra's algorithm maintains the length of the shortest such path to v in a value called d of v. So d of v is the best known distance to v for the current set of vertices capital S. At each stage, Dijkstra's algorithm finds that vertex u which has the minimum d of u value. This is what I said when I was describing the algorithm working on the particular example, but it looks for that vertex u which is not on the source side, which has the smallest d of u value, and brings that vertex into capital S. Once it brings that vertex into capital S, so what happens is that here is capital S, and here is v minus s, and u has just been brought into capital S. And now what it says is it needs to update the distances of all the vertices here. Remember, for each vertex here, v, we are maintaining a quantity called d of v. So it needs to update those distances. So for example, for this v, it needs to update its distances. And the updates need to happen depending on the edges that are incident on u. So for example, for each edge u like this, uv like this, it may need to update the distance to that vertex v.